Isotopia, we are going to discuss what isotopes exist and why. Which ones are stable and which ones are unstable. So we should be able to read and interpret the isotope graph that you guys have in front of you now. We should be able to figure out how many isotopes exist based on the graph. We'll also review isotope notation and figure out what isotopes are radioactive. We'll talk about a little bit more about that later. So an element, remember, this is review, don't take this down, is defined by the number of protons indicated by the atomic number. So like in the periodic table, we have carbon, its atomic number is 6, meaning that every single carbon atom has 6 protons. It's mutually exclusive, so that if you have 6 protons, that means you're a carbon atom. Okay? So there's a little, and these nuclei are transferred all over the place. So they're the building blocks of all the matter, and these nuclei are transferred all over the place. And they're held together by the neutrons inside the nucleus and the strong nuclear force. Okay? So they have all these cycles. So carbon is, and each one of these is represented by a proton. This is a carbon nucleus. So carbon has 1, 2, 3, 4, 5, 6 protons. But most carbon has 6 neutrons as well, giving it a mass of 12. But some carbons have 7 neutrons, and even some have 8 neutrons. Carbon 13 and carbon 14. These are all collectively, they're all the isotopes of carbon. There are 3 isotopes of carbon, meaning that we have carbon atoms with a mass of 12, 13, and 14. Okay? Because they have different numbers of neutrons. And neutrons have mass. So they can vary. The abundance, like we talked about, the overall average has to do with the mass, 12, 13, and 14 respectively, and the abundance in the percentage, about 99, about 1, and less than 0.1%. Kind of like we talked about in the activity day. Can you guys all look up here? Gabby, can you look up at the board? Thank you. Stop that. Thanks. So, moving forward. And remember, the key thing is, what's true about all carbon atoms? What do they all have? They all have 6 protons. The neutrons can be different, the electrons can be different too. But they have 6 protons, that's the key. So, all of these are the isotopes of carbon. It's just an atom with a certain mass. Kind of like we had pennies today. They're all pennies, right? What varied? The mass. We have the different types of pennies we had. We had 3.1 gram pennies, 3.0 gram pennies, 2.5 gram pennies, and 2.4 gram pennies, right? And then we had a little variation, but that's because of the differences in pennies. They wear differently, so there's going to be some variation. So isotope notation is a shorthand way of writing it. So this is carbon 12. That's how we write carbon with a mass of 12. That's how we write carbon with a mass of 13. That's how we write carbon with a mass of 14. Okay? The superscript before it denotes the specific isotope. So if you're talking about carbon 12, you're talking about that carbon up there. On the periodic table is the average of all of them. Kind of like how we found our average in our mass of pennies today. So, moving forward. Atomic mass number is the average. This is all review, guys. So, all chlorine atoms have 17 protons. Chlorine 37 has 20 neutrons. This is how we figure this out. Because the total of 17 plus number of neutrons is 37. Number of neutrons has to be 20. Okay? Not all of them are stable. Carbon 12 will form, but never carbon 11. So carbon 11 isn't an isotope of carbon because it doesn't exist. And that's what we're going to figure out today. And you guys take a look at this chart right in front of you. on this table right here. And pay attention right now. Okay? Look up here. This is going to be explaining what we're doing. So, each box represents an isotope of an element. So, for instance, look at your periodic table, atomic number 1. So, take out your periodic table for a second. I'll pause this. So, atomic number 1 is hydrogen. So looking at this box, there are 3 different types of hydrogens. So look up, this first box is hydrogen with 0 neutrons. Second one is hydrogen with 1 neutron. Third is hydrogen with 3 neutrons. So the mass is indicated by the top corner right here. So 1 plus 2 is 3, and that's where we get the mass up here. So each of these are the 3 isotopes of hydrogen. Take a look up at helium right here. So, Bray, how many boxes are there for helium? 1. That means there's only 1 isotope of helium. The only type of helium that exists is helium with 2 neutrons. All helium has 2 protons and 2 neutrons. What about atomic number 3? Antonio, what's atomic number 3? What element?
What element?
Yep. Lithium. So lithium with 3 protons has 2 different isotopes. It has isotope with 3 protons and 3 neutrons, indicated by the axis. The y-axis is the number of neutrons. The horizontal axis is the number of protons. So we have 3 protons and 3 neutrons. So what would that mass be, Divine? It would be 6. Total of 6. What about the mass of 3 protons with 4 neutrons? What mass number would that have, Connor? If I had 3 protons and 4 neutrons, what mass would that be? 7. So I have 2 different types of lithium. I have lithium 6 and lithium 7. So right now I want you guys to finish filling in this chart right here with all the other elements. I'll pause for a second. So you guys want to fill the rest of this in. So helium has 1 isotope. Lithium has 2. So if you guys look at this graph, this is the same graph we had before. Atomic number is the number of protons. Now, you can get the different isotopes there. Each box represents an isotope. So if you look up at atomic number 20, atomic number 20 is calcium. So if you look at this calcium number of protons, you have 1, 2, 3, 4, 5, 6 boxes. So you have calcium with 20 neutrons, 21, 22, 23, 25, and 27 neutrons. So you have all those different isotopes. The most abundant one is the one that's shaded in dark. And the other ones that are found are shaded in light. And the radioactive isotopes, which aren't stable, those ones are listed as clear. So those ones aren't stable for a long time. They're going to break up. They're not stable nuclei. They're going to explode. We'll talk about radioactivity next.